We have learned that the voltage and current waveforms, be it AC or DC, in power electronic circuits do not look like their ideal counterparts. A DC voltage in power electronic circuit does not mean that the magnitude of the voltage doesn't vary with time. Similarly, an AC current in a power electronic circuit does not necessarily have a sinusoidal variation. We have also learned the ways to quantify the periodic waveforms by defining certain measures. As seen in the previous lecture, some of the waveform measures quantify the closeness of an AC or DC waveform to its idealized version. For example, the waveform with less ripple factor is close to an ideal DC waveform. The waveform with less total harmonic distortion is close to an ideal AC waveform. But why are we so concerned about the waveforms being close to ideal? What is the significance of these clean waveforms? Let us try to understand this with some examples. Let us consider a power electronic converter which is supplied from a DC voltage source. The DC voltage source can be considered as ideal. For example, a battery. Its voltage does not vary that fast with time. And this voltage source is supplying a load through a power electronic converter. The input voltage to this power electronic converter is shown as a straight line because it doesn't vary with time, V in. And the input current, let us say, for example, we consider that it varies as this I in shown here, which has a triangular variation with an average value I in AV. Now let us try to look at the power that is flowing into the power converter or the power that is coming out of the DC voltage source. So power, we know that it's a product of voltage and current. So if we take the product of voltage and current over time, it looks like this. It looks like the third waveform that is shown on the left side. So P in is equal to V in times I in, and it is also a triangular waveform because it's a product of V in and I in, and it also will have an average value V in into I in average. Now let us try to look at the net energy supplied by the source. What is the net energy supplied by the source over this time t, capital T? T is the periodicity of this current, so it will also become the periodicity of the power. So the net energy supplied by the source is the area shaded here. So that area is equal to V in into I in average multiplied by T. The product V in into I in average is referred to as average power, P average here. Now let us take a look at the components of the current waveform. The current waveform is periodic. I in is periodic. It's varying like a triangular wave. It will have an average value which is equal to I in average, and whatever is remaining is termed as the ripple here, I in tilde, denoted by I in tilde. So I in is equal to I in average plus I in tilde, and I in tilde is a triangular waveform with zero average value. So if we see the ripple component, it does not really contribute to the average power. The average power that is supplied by this DC voltage source is equal to the average value of current multiplied by V in. So the ripple components do not really cause a net energy transfer happening. That is why we have been referring to them as unwanted components. So if we have an ideal DC voltage source, we would like to have no ripple in the current drawn from that source. And what do we mean by ripple here? Any component other than the average. So when we deal with DC quantities, any component other than the average is considered as ripple, and it is undesirable from the point of view of power transfer because it does not cause any net energy transfer. Now let us consider a power electronic converter which is connected to an AC voltage source on the input side, and it is delivering some power to the load on the other side. This AC voltage source can be considered ideal. That means the voltage is purely sinusoidal. utility, the utility or grid can be considered as an example. So Vin can be expressed mathematically as Vm sine omega t, and it can be shown graphically by a sinusoid. And In, the input current drawn by the power electronic converter from the ideal AC voltage source, is varying as a square wave in this example. And the frequency of this square wave is same as that of the input AC voltage. Now let us look at the power drawn by the power electronic converter instantaneously at any given instant. So if we want to look at the power, we need to multiply voltage and current. That means we need to multiply the two waveforms of voltage and current, and when we multiply, it results in the third kind of plot shown on the left side. So this plot, and its peak value is Vm Im, and it has a periodicity of twice the input frequency. And what is the average value of that? The average value of this power, input power, is 2 Vm Im by pi. The net energy supplied by the source will be integral of this power, integral 0 to t p in dt, which is equal to 2 Vm Im by pi multiplied by t. Sorry, this t was not there earlier. So the net energy is given by 2 Vm Im by pi multiplied by t, and this product 2 Vm Im by pi is referred to as the average power. Let us take a look at the components of the input current waveform, just like we did in the other example. So if you consider the square wave input current waveform In, which is shown separately here, it has a fundamental component drawn in purple color. And what is the peak value of the fundamental component? It is 4 Im by pi. So In1 is equal to 4 Im by pi sine omega t. And the nth harmonic component, any nth harmonic component, we know that the square wave does not contain even harmonics. It has only odd harmonic components, third harmonic, fifth harmonic, seventh harmonic, and so on. And the magnitude of any nth harmonic component is 1 by nth of that of the fundamental component. So I in n is equal to 4 Im by n pi into sine n omega t. So if we express the current mathematically, In is equal to 4 Im by pi multiplied by sine omega t plus 1 by 3 sine 3 omega t plus 1 by 5 sine 5 omega t, and so on. And we know that the input voltage Vin is equal to Vm sine omega t, which is a pure sinusoid. Now let us look at the product of these two. Pin is equal to Vin times In. So it will be 4 Vm Im by pi multiplied by sine omega t multiplied by sine omega t will give sine square omega t, and sine omega t multiplied by sine 3 omega t will give sine omega t into 3 omega t, and sine omega t multiplied by 5 omega t, and so on. So there will be many terms, ideally infinite terms. So which of these terms has a finite average value? Only the first term, the sine square omega t term. And what is the average value of that? The average value of sine square omega t is 1 by 2. Let us look at the other terms. Sine omega t multiplied by sine 3 omega t. This product can be written as a sum which contains sine 2 omega t and sine 4 omega t, and the average value of both of them is 0. Similar is the case with the third term, sine omega t sine 5 omega t, that can be expressed as sine 6 omega t and sine 4 omega t, and again the average value will be 0. So which component of current is contributing to the average power? Here the fundamental component of current is contributing to the average power. And what is the frequency of the fundamental component of current? It is same as the frequency of current waveform. And what is the frequency of current we considered? We considered the frequency of current waveform to be equal to the frequency of input voltage waveform. That means the voltage and current having similar frequencies will only contribute to the average power. If voltage and current have dissimilar frequencies, they do not contribute to any average power. That means they do not cause any net energy transfer. So from the viewpoint of net energy transfer, it is again desirable not to have ripple components even when the voltage source is an ideal voltage source, ideal AC voltage source. And what do we mean by ripple here? In the case of an AC voltage source, in the case of an AC voltage source, that means when your power converter is connected to an AC voltage source, any component other than the fundamental component of current, and again the fundamental component should have the same frequency as that of the input AC voltage source. So any component of current that has frequency other than the frequency of input AC voltage is considered as ripple, and that is undesirable because it does not cause any net energy transfer. It is worth to note that even if the current waveform is sinusoidal, only the component of current which is in phase with the input voltage can actually cause a net energy transfer. The component which is out of phase with the input voltage will not cause any average power transfer, and the out of phase component is popularly known as the reactive component of current. So the reactive component of current is also undesirable from the viewpoint of net energy transfer. To summarize, the component of current which is having the same frequency as input voltage, input AC voltage, and is also in phase with the AC input voltage will only cause net energy transfer. The ripple currents are undesirable from another perspective. So let us consider this power electronic converter, and let us say it has some circuit element RE, and for simplicity let us assume that it is in series with the input terminal, and RE is the resistance of this circuit element and IE is the current flowing through this circuit element, and it is the same as the input current. Any circuit element will typically have a resistance because of the material properties, limitations on the material properties. Even if we have a inductor is made of wire and core, and that wire is made of copper, and copper has a finite resistance. So any circuit element typically has resistance. Even the capacitors have something called equivalent series resistance. So when there is resistance, there will be power loss in the circuit element, and that power loss is given by IE RMS square RE. Again, what is the power loss? This power loss is the average power loss. On an average, IE RMS square RE amount of power is lost in the circuit element. And what is the total value RMS consist of? It consists of IE average square plus IE tilde RMS square. So that is the RMS value of the ripple component of the current. So this RMS value of the ripple component of current causes additional power loss as shown here. We can also understand this in AC circuit. So in the AC circuit, if the current waveform is square wave, it contains fundamental component, third harmonic, fifth harmonic, and these harmonic components will cause additional power loss as indicated by this expression. The ripple components of currents are undesirable from yet another perspective. This applies to AC circuits primarily. Let us say we have an equipment which requires a sinusoidal voltage. We have a load drawn in black color. It requires a sinusoidal voltage to be applied. And assuming that the grid is a sinusoidal voltage, we directly connect the equipment to the utility. But we have to keep in mind that we are dealing with time varying currents, and time varying currents produce time varying flux, and time varying flux again induces voltage. So we can define inductance in the elements where time varying currents are flowing. So this Ls represents source inductance. It can represent the inductance of the whole network, the wires that are coming all the way to the equipment from the utility. Even though it is insignificant, like a few microhenries, it is present. Let us say we have a second load shown in green color, load 2, which requires the power to be supplied at another voltage level. That is why we have brought in a power electronic converter to match the voltage levels. And the input side of the power electronic converter is the grid voltage, and let's say the power electronic converter starts drawing square wave kind of current, which has fundamental component as well as ripple. The ripple is a collective term for all the harmonic components. So if we apply KCL here in this node at which both equipments are getting supplied, IS is equal to IA plus IB, and IB can be expressed as the sum of fundamental component and all the harmonic components. So let us say it is IB1 plus IB tilde. And what is the voltage now that is getting applied across the load 1, which is VA? VA is Vs minus Ls d Is by dt as given by the KVL. So now if we express Is in terms of Ia and Ib, VA will be equal to Vs minus Ls d by dt of Ia plus Ib, and Ib we have seen that it is non-sinusoidal. Since Ib is non-sinusoidal, Va will definitely be non-sinusoidal. So the ripple currents, the harmonic currents, ripple currents drawn by the power electronic converters distort the voltage that is getting applied to neighboring equipment, which is undesirable. To summarize, why are we concerned about the waveforms being clean, and what do you mean by clean? An AC waveform being close to sinusoidal and a DC waveform being close to a non-time varying waveform. Why? Because ripple currents are undesirable as they do not contribute to net energy transfer, and they cause additional power loss in circuit elements, and they also distort the voltage applied to neighboring equipment. So because of these undesirable qualities, ripple components have to be avoided. So we are concerned about minimizing those ripple components, and when we have an AC periodic waveform or a DC periodic waveform, we'd like to quantify the undesired component. That is why we have seen all these waveform measures.